Have you ever wondered how GPS knows exactly where you are? Or how rocket scientists calculate the perfect trajectory to Mars? It all starts with understanding one simple but powerful concept: displacement. Today, we're diving into the foundation of all motion analysis. We'll discover how physicists simplify complex objects into points, learn the crucial difference between distance and displacement, and see why direction matters as much as magnitude in physics. By the end, you'll think like a physicist when describing motion. Our learning objective today is to describe changes in an object's position using the object model and displacement. When you look at a car driving down the highway, what do you see? A complex machine with doors, windows, wheels, and countless moving parts. But here's the physicist's secret. We ignore all of that. In physics, we use something called the object model. This means we treat the entire car as a single point particle. The size, shape, and internal configuration are completely ignored. Why would we do something so seemingly ridiculous? Because it works beautifully for analyzing motion. Quick pause. You're watching this because it was created on EulaIQ. EulaIQ instantly transforms your textbooks, PDFs, or notes into explainer videos, podcasts, or practice questions. Imagine turning your study materials into learning content you actually enjoy. That's what EulaIQ does, and you can try it now for free at EulaIQ.com. Picture a tennis ball flying through the air. Its fuzzy surface and spinning motion don't matter for basic trajectory calculations. What matters is tracking one point, usually the center of mass. This point carries all the object's extensive properties: mass, charge, energy. But the detailed structure vanishes from our equations. This simplification lets us focus on the essential physics of motion. Now, let's talk about displacement. This is where physics gets its first dose of mathematical precision. Displacement is defined as the change in an object's position. We write this as delta x equals x final minus x initial. The Greek letter delta always means change in throughout physics. But here's the crucial insight. Displacement is not the same as distance traveled. Let me show you why this distinction matters. Imagine walking from your bedroom to the kitchen. You might take a winding path through the hallway. Maybe you backtrack to grab your phone. The total distance you walked could be 50 feet, but your displacement? Just the straight line distance from bedroom to kitchen, perhaps only 20 feet. Displacement only cares about starting point and ending point. Everything in between is irrelevant. Here's where displacement reveals its true power. Displacement is a vector quantity. This means it has both magnitude and direction. If you move 10 meters to the right, your displacement is positive 10 meters. Move 10 meters to the left, your displacement is negative 10 meters. The magnitude is the same, but the direction makes them completely different. Let's work through a concrete example. A car starts at position 30 meters on our coordinate system. It drives to position 52 meters. The displacement equals 52 minus 30. That's 22 meters in the positive direction. Now the car reverses course. It ends up at negative 53 meters. What's the displacement from the 52-meter position? Negative 53 minus 52 equals negative 105 meters.
These concepts aren't just academic exercises. GPS systems use displacement calculations to track your movement. Engineers designing roller coasters need to know the displacement between track points. Even your smartphone's step counter uses displacement concepts. When you track your morning jog, the app calculates both your total distance traveled and your net displacement from home. Understanding this distinction helps you interpret the data correctly.
Before we can measure any displacement, we need to establish a coordinate system. This is our reference frame for describing motion. We choose an origin, a starting point for our measurements. We define positive and negative directions. Without this framework, position and displacement have no meaning. Different observers can choose different reference frames, but once chosen, all measurements must be consistent with that frame. Let's wrap up what we've discovered. The object model simplifies complex objects into point particles. Displacement measures the change in position, not distance traveled. As a vector quantity, displacement includes both magnitude and direction. Coordinate systems provide the essential framework for all measurements. In our next video, we'll explore how displacement changes over time. We'll discover velocity, the rate of change of position, and learn why average velocity and instantaneous velocity are two very different concepts. Before you go, here's the best part. This video wasn't handmade. I just uploaded a PDF and EulaIQ turned it into this explainer automatically. You can do the same with your own notes or textbooks, and in seconds get a clear video, an audio lesson, even quizzes. Start for free today at EulaIQ.com and make studying effortless.